This is a synthesis problem, so we should step back and analyze what we have and look at how we can solve it. This is a very general synthesis problem for which there are many different solutions. Okay, so I'm just going to pick one arbitrarily. There may be better ones, and I'm sort of going to pontificate on what other alternatives there might be. But as you can see, they're both acyclic, so we don't have to mess with any cyclizations or anything like that. We have a starting material that is 1, 2, 3, 4, 5 carbons. We have a product that is 1, 2, 3, 4, 5, 6, 7 carbons. So somewhere along the line, we have to add 2 carbons. In the starting material, the functions are at the termini. So in the product, they are almost well, this one is at the one terminus, and this one is almost at the other terminus, 1 over. So it seems logical to look at this as a problem where one function at one end is transformed into the other function at the one end of the product, and vice versa for the second function. Okay? So I'm going to arbitrarily pick this as being the source of the aldehyde, and the alcohol being a source of the extra 2 carbons in the carbonyl. But if you look at it for a while and you work with this, and I urge you to do this, at home, trying to find different solutions, you can do it actually the other way around also. Okay? So there are 2 options. So with this analysis in mind, the first question is, do you have any chemistry in mind that might be doing this? And one way to, obviously, since this is an alcohol, to somehow add 2 carbons is to use organometallic chemistry that adds those 2 carbons to some kind. Obviously, you can't do it to the hydroxy directly, but to some functional derivatives of the hydroxy. The second one, the other end, is an acetylene, and it has to be turned into an aldehyde, and that should trigger your memory banks because there is a reaction that turns terminal acetylene into the aldehyde, and that is hydroboration oxidation. Okay. So with that in mind, we can look at the retrosynthetic analysis of this, where strategically, I'm going to use the acetylene as the aldehyde precursor. And you see, I'm talking very generally without worrying at the moment about the exact details. Okay, once you get into the details, you have to worry about protecting groups and the like. So I'm going to do that. And the second one on the left, I'm going to cleave like that and introduce a 2-carbon piece that either directly makes the ketone or is some kind of masked ketone that will do that. So bearing that in mind, it's a ketone. The first thing that should come to your mind is, well, I've got a whole bunch of ketone synthesis now that I know. You can pick any one of them. You have ketone synthesis where the function R, C, O, R dash can be disassembled at will, either this way or that way. Okay? And just to give you a couple of them, one of them is something we learned last Thursday, nitriles. Okay? You can go by a nitrile, either R, CN triple bond and add a Grignard from the right, or we do R dash CN triple bond and add a Grignard from the left. Similarly, a complementary approach can be taken from an ACl halide. We know that ACl chlorides with cuprates make ketones. And then, of course, there's always these old standby, chapter 8, we can get to ketones through addition chemistry and alcohol oxidation type reactions. So I'm going to use an approach where I'm going to add the methyl group, this is arbitrary, there may be quicker ways of doing this, as a Grignard to a nitrile that I'm introducing at this carbon here, taking advantage of the fact that we have a hydroxy function here that I can turn into a halide. Okay? So retrosynthetically, this means that in a step where the aldehyde is already preformed, I need to perform an organometallic reaction on the left. And therefore, this means that I will have to protect the aldehyde as the acetal. And then, retrosynthetically, I'm going to cleave here, which means that, hang on, so I'm going to do the shorter way where I'm going to use an acetonitrile equivalent. That's more obvious. Where I'm going to use a Grignard and there you can see we need the protection on the right, because otherwise you can never form this Grignard. And acetonitrile. Okay, so that anion will attack here, make the imine, which we don't isolate, we just dump in acidic water on the imine anion, makes the imine, and then it hydrolyzes the imine to the corresponding ketone. And so obviously then, retrosynthetically, this guy would be the corresponding bromide. And that will come from the corresponding alcohol. And that will come from the corresponding aldehyde. And that will come from the corresponding starting material, acetylene. So in the forward sense, what we're going to do is do a hydroboration oxidation. I don't have space there, so I'm going to write it here. 1 borane, 2 H2O2, hydroxide. That gives the aldehyde. Then I'm going to protect. So I'm writing the actual forward steps with an arrow, although I'm actually going backwards. So think of it as a forward scheme. Ethylene glycol plus H plus. And then here we're going to use PBr3, turn the hydroxy into a bromide. And here, obviously, we're going to use magnesium. Sorry, this way. Magnesium to make the Grignard. And then this is basically just aqueous workup. So this is just the 2 mixed together. That's enough. There's no further reagent because aqueous acidic workup is implied. That makes that ketone. And then here we need to hydrolyze. That makes the aldehyde. And the last step is What am I doing now? Oh, no, that's it. Yeah. That gives us the corresponding product. So, as I said, alternatives are possible. You can putz with this triple bond and turn that into the acetyl group if you want, okay? Which means that you would have to add 2 carbons on this end, which you can do in a variety of ways, using organometallic chemistry on the aldehyde of this, or you can oxidize this to the carboxylic acid, make the acid chloride, and then do cuprate additions and so on. Okay? So it's very variable, this problem. Many different solutions. They're all right. Okay, so we finished, or started at the end of last lecture with looking at physical properties of the amines. And one thing that I pointed out is that amines, which you can view as a nitrogen with 3 substituents plus a lone pair, which one can count as a 4th substituent, they're configurationally unstable. They undergo very fast enantiomerization, or what's called inversion. That is, this electron pair essentially swings through the nitrogen atom to the other side. It tunnels through the atom. This movement is very reminiscent of the transition, or the process for an SN2 reaction, okay? Where we come in with a nucleophile, and we kick out a leaving group, and the orbital that was used, the hybrid orbital that was used to the leaving group inverts in the transition state. Okay? So in a way, you can view this as if it were an intra-atomic SN2 by the lone pair as it swings through the atom to the other side of the molecule. The activation energy for this is very, very low, 5 to 7 kilocalories, which means that if you wanted to freeze this out to prevent the amine from inverting, you would have to cool to minus 130, minus 150 degrees Celsius. Okay? So at room temperature, this is an incredibly fast process. And the consequence of this is that if you have a chiral amine, that is a nitrogen that now has 4 different substituents, if you count the lone pair as a substituent, in this case methyl, ethyl, hydrogen, and the electron pair, it's not stable as such because it inverts to the mirror image. So there's image, mirror image, and they interconvert very rapidly. So in general, amines cannot be resolved and kept in the unresolved state. Okay? The exception is, as we already saw in some of the alkaloid natural products, like morphine, for example, structure that we saw earlier, is when you embed the nitrogen in some polycyclic frame where inversion is sterically not possible. Okay? So if you link if you make this an alkyl group and you link all 3 groups such that you have some kind of a cage in the back, then the nitrogen can't invert into the cage. It's fixed. Okay? So that kind of nitrogen can be made optically active, and in nature it exists as only one enantiomer, since nature, by and large, prefers only the image, not the mirror image, of 2 compounds, with some exceptions. Obviously, sometimes they're racemates and so on. And so sometimes one species produces one enantiomer, another species produces exactly the opposite enantiomer. And you can see here the swinging through the transition state for this inversion, which looks very much like, with the nitrogen sp2 hybridized, it looks very much like the SN2 transition state, except that we have nothing on the right and nothing on the left. There's no nucleophile that comes in on one side and no leaving group that leaves on the other side. And as I said, the nucleophile, as it were, is the electron pair that swings in and then it leaves on the other side, okay, to make this guy. So a consequence of the electron pair on the nitrogen is that the nitrogen can be both basic and nucleophilic. And I briefly mentioned at the end of last lecture that the 2, as we should remember from chapter 6, are really the same. It's a definition. They refer to what is being attacked. So when the lone pair attacks a proton, you push an arrow towards H and kick out chloride, in that case we call the amine lone pair as acting as a base. When it attacks anything else but a proton, we call it a nucleophile. But the processes are identical in terms of electron pushing. So we push an electron pair to H, chloride flies out, or we push an electron pair towards carbon, and iodide flies out. Okay? When we do it to carbon, we get ammonium salts. Now, one of the neat things about ammonium salts is ammonium salts, since they're tetrasubstituted nitrogens, there's no lone pair left, it's been tied up in bonding to a carbon, are now configurationally stable. Okay? So, and that is a way to resolve amines as ammonium salts that are stable and do not undergo racemization. And so what happens is, what you typically do is you take an amine, it's a chiral amine, so here I have ethyl, phenyl, methyl, and the lone pair, and it undergoes fast enantiomerization through inversion through nitrogen, and you trap that lone pair with, or you alkylate the nitrogen with phenyl methyl chloride. This guy, as we shall see in the next chapter, exhibits properties very much like an allylic chloride because it's got double bonds next to that carbon, and so that it imparts the same kind of reactivity as allylic halides. And so you do an SN2 on this guy, and that gives you the ammonium salt, sometimes referred to as the quaternary ammonium salts because it's all alkyl groups all around the nitrogen. And when you trap this guy, you get this ammonium salt. And when you trap this guy, you get this ammonium salt. And there's a 50-50 chance of trapping either one, since it's a racemate over here. And so you get a 50-50 mixture, a racemic mixture of the 2 ammonium species. But now these 2 guys do not interconvert. Okay? And that gives you a handle towards separation of the 2 enantiomers. And as you may or may not recall, one way to separate enantiomers is to use a chiral auxiliary, a compound that is optically active and it has handedness, and it's only imaged rather than mirror image, or only the mirror image. It's only one of them. And you make a bond to racemic mixture of 2 enantiomers. And the handed auxiliary adds other stereocenters to the picture, which are defined, making this a diastereomeric mixture. Now, diastereomers are different compounds. They have different boiling points, different melting points, different chromatographic behavior, different NMR spectra. And so you can separate them by standard separation techniques. So in the case of ammonium salts, one thing that's often used, because it's a cation, is that you exchange the anion, whatever it is, in this case it's chloride, with a chiral optically active anion. Some negatively charged natural product, typically a carboxylic acid or sulfonic acid, like camphor sulfonic acid or something like that. Or if you want, since we did lysergic acid last week, you could use lysergic acid as the carboxylate, as the counterion. So you dump in lysergic acid carboxylate into this, and it will attach itself to both of these species and now turn them into diastereomers, and from which you can separate one over the other by fractional crystallization, for example. So the situation is very much like you in the dark in the morning your lights aren't working or something, or you don't want to turn the lights because whoever is sleeping with you in the room doesn't want to be woken up, and you're grabbing your shoes, okay? And let's assume you have 20 pairs of shoes. Probably don't, but in a few years you'll have 20 pairs of shoes. You go in the dark and you poke around, and your hand, which is your chiral auxiliary, that's the lysergic acid carboxylate compound, will be able to tell the difference between a left shoe and a right shoe. And that way you can pull out one left shoe and one right shoe. And you may even be able to tell what kind of shoe it is if you have 20 different pairs of shoes. And that way you separate exactly by that principle. That's exactly the principle that's used with these chiral auxiliaries. Once you have them separated, you put one on the left and one on the right. Now they're separate, and you know where they are. This is what you do when you do fractional crystallization. And then you exchange the auxiliary back to chloride. But now on the two compounds in two different flasks, so that way you can separate one enantiomer from the other. So that's what is possible in the ammonium salts because they are configurationally stable. Okay, another aspect of nitrogen is, as you know, it's to the left of oxygen. So compared to the classic hydrogen bonding motif, which is water or alcohols, which we encountered in chapter 8, where the typical water-hydrogen bond is worth about 5 kilocalories per mole, we also have hydrogen bonds with amines, but the nitrogen is less electronegative, so there's less delta plus on these protons, and therefore these bonds are weaker. And so there's less, this is basic Coulomb's law in action, in a way. And the energy of these bonds is about half that, roughly, of that of the OH-type hydrogen bonds. Nevertheless, amine hydrogen bonds are abound in nature because in most natural products where it's significant, such as, for example, the polypeptides, and we saw a picture of hydrogen bonds and a polypeptide, there are multiple hydrogen bonds. So if you have 100 of 3 kilocalorie bonds, that's 300 kilocalories. That's easily enough to enforce some three-dimensional structure that would normally not form, and we'll come back to that in the last chapter. And so these bonds are a little weaker. Another consequence of this, where it's also blatantly obvious, the boiling point of ammonia is minus 33 degrees. Compare this to the boiling point of water. Yeah, there's just one mass unit difference between ammonia 15 and or 17 and 18, I guess, and no, it's the same, and water 18. Okay? So water has a boiling point of 100, okay, which is actually the anomaly. That's extraordinary for a small molecule like this to have such a high boiling point. And the entire reason for that is hydrogen bonding. Yeah.
So like how many calories less are the bonds compared to like
about half, so 2 to 3 per NH bond, as opposed to about 5.5 for OH bonds. So water boiling point 100 is why life on this planet has evolved the way it has, by the way, of course. That's why we have oceans. And that's because the water molecules in water are not alone. They all form hydrogen-bonded networks in all directions. And that makes it difficult for relatively speaking, for the water molecule to lift into the gas phase at room temperature. You have to heat to 100 degrees before it really starts boiling away. And so that's a huge difference between plus 100 and minus 33. Now compare water and ammonia, both of which do hydrogen bonds, with something equally sized that has no hydrogen bond, methane. Now, methane, no hydrogen bond, that thing boils at minus 180 degrees or something like that. Very, very low temperature. Can't remember the exact number, but it's in that regime. So you can see that hydrogen bonding plays a big role, particularly if there's several that help the molecules stick together. Now, one other reminder for alcohols, and of course for water, water has 2 H's that can form hydrogen bonds. Alcohols have 1. If you replace the H in an alcohol with an alkyl, you get an ether. Ether have no hydrogen bonds. So dimethyl ether, again, has a very low boiling point, okay, as opposed to methanol. And a similar thing pertains for amines. You can only form hydrogen bonds if you have a proton sitting there. So ammonia is okay, primary amines and secondary amine, but tertiary amines with 3 alkyl groups cannot be proton donors because they have no protons in hydrogen bonds. They can still be acceptors, okay? So they can form hydrogen bonds to water, for example, okay, but not donors. Okay, so let's talk a little bit about acidity and basicity. Amines can be acidic, and this is in comparison to alcohols. Remember, we started all this saying one can view amines as nitrogen analogs of the alcohols, and there are some similarities, except that there are also strong differences because nitrogen is much less electronegative. Okay? And so alcohols, remember the pKa of alcohols was around 15, 15 to 18. We settled on 15 as a good round number, similar to water, same as water. And so what is the pKa of something like this? So you set up the acid-base equilibrium, which involves measuring the dissociation of this as a proton in water, which means you're protonating H2O to make H3O+, and you get the amide anion. In this equation, if water is the solvent, the concentration of water stays unchanged. So in order to determine the pKa, we don't measure the direct equilibrium constant, or you measure the equilibrium constant, you turn the equilibrium constant in a so-called acidity, acid dissociation constant, where the concentration of water has been pulled out. Concentration of water in water is the molarity of water. It's 1,000 divided by the molecular weight of water. It's 55.5. So there's a factor of 55.5 that is pulled out of the acid dissociation equilibrium. Remember, if this were the normal equilibrium constant, it would be the product of the concentrations of these two guys divided by the concentration of these two guys. But notice, the concentration of water isn't in here. It's actually been pulled out into the Ka, so there's a factor of 55.5 there, just to remind you of where this comes from, because some of you going to biology, biochemistry, will see these kinds of equations, and if you're in the lab, you might actually even have to apply them. So